So in section 8.6, we started to develop ways of representing certain functions as power series. And we did that using a couple of different techniques. We either did it algebraically, taking the Taylor series, the power series for some known function and doing some sort of algebraic substitution or multiplication in order to rewrite um, that power series as a power series for some other function. For example, when we did 1 over 1 minus x, we were able to develop the power series using long division. And then if we wanted the power series for 1 over 1 plus x, we just made a substitution, substituting negative x in for the x, and we ended up with a power series for the new function. We also did some other techniques. We used calculus. We took derivatives to generate power series for the derivative of 1 over 1 minus x, or we took an antiderivative and generated a power series for the antiderivative. And so those techniques are still at our disposal, and they're solid techniques that we want to be able to utilize because they're actually very efficient compared to what we're about to learn. But we do want a general method for generating power series for series that or for functions that aren't directly related to the power series that we know. So we have a very limited scope, a very limited class of functions that we could apply these algebraic and calculus-based techniques to. We want a more general technique. So this is where Taylor and Maclaurin series come in. Now, let me be clear from the start. Taylor and Maclaurin series are power series, but they have these special names based on just some mathematicians in the history of mathematics. And Taylor and Maclaurin series themselves are related to each other in a certain way, which we'll get to later in this section. So we're just dealing with power series, and we're looking for a general method for generating power series for other functions. So let's start by letting f of x be a function represented by a power series. So, c sub 0 plus c sub 1 times x minus a plus c sub 2 times x minus a squared and so forth. You get out to c sub n times x minus a to the n. So this is a power series centered at a, and we're just going to, say it converges on some interval that whose absolute value of x minus a is less than r, some radius of convergence. And we want to figure out some relationships from this equation here from this power series on how we can relate back to the original function. Now remember, to determine a power series, I need to figure out these coefficients. This is really what we need to do. I need to figure out c sub 0 and c sub 1 and c sub 2 all the way down the line. And if I can figure out all the coefficients for a particular function, and of course know the center at which I'm orienting this power series, then I'll know the power series for that function. Then I'll just have to figure out where it converges. So our goal right now is to figure out a way to represent all of the coefficients in our expression here in terms of the function that we are dealing with, okay? Now the function we're dealing with right now is just f of x, and then we'll of course be able to apply it specifically to examples that we'll look at later. So let's start with something very, very simple, okay? If I just let for a moment x equal a, then what do I get? Well, over here, of course, I get f of a, and then on the right-hand side, well, c sub 0 is still there, but c sub 1 is going to be multiplied by a minus a, which of course is 0, and then c sub 2 is multiplied by a minus a squared, which is still 0, and all the terms after that is going to be 0. So very conveniently, our constant here is just f of a, whatever our original function is, evaluated at the center. And that's our first coefficient, the constant, if you will, of our power series. Oh, that was nice. So how are we going to generate c sub 1? Well, there's a lot going on here, but I could simplify it. Well, I could simplify part of it and make other parts more complicated if I do a little calculus here. Let's take a derivative. What is f prime of x? Well, of course, the derivative of c sub 0 is 0, and the derivative of c sub 1 times x minus a is just going to be c sub 1. And then we're going to have plus 2 times c sub 2 times x minus a. Remember, a is a constant, so the derivative of x minus a is just going to be 1. plus 3 times c sub 3 times x minus a squared plus dot 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 plus n times c sub n times x minus a to the n minus 1 plus dot dot dot. Excuse my neighbor's dogs in the background. All right, now with that in mind, let's do the same thing. Let's let x equal a, and then that'll tell me that f prime of a is going to be equal to c sub 1 plus, again, the second term is going to go to 0, as will the third and all the rest that follow. So f prime of a is going to equal c sub 1. Well, that's kind of cool too. You may want to try to guess what c sub 2 is going to equal, but be careful here. It's not as straightforward. You only have 2 points. It's going to be important to not generalize prematurely from just 2 pieces of data. All right, well, I need to figure out something for c sub 2, so let's take another derivative. F double prime of x, the c sub 1 will become 0, and then I'm going to end up with 2 times c sub 2 plus, now I'm not going to multiply the 2 and the 3, I'm not going to simplify the multiplication of 2 times 3 as 6. I'm going to leave this separate, and you'll see the reason why later. So it's going to be 2 times 3 times c sub 3 times x minus a. Let's imagine what the next term is going to be, just to make, we're going to need it in a moment. So the next term would have been, if we would have kept going up here, it would have been 4 c sub 4 x minus a cubed. Now, if I take the derivative of that one, the cubed, the 3 and the x one, it becomes now down as a multiplier, times 4 times c sub 4 times x minus a squared plus, and then I'm going to have n minus 1 times n. Whoops, I forgot all the dot dot dots in there. I think I'm just trying to squeeze it all on the screen, and I'm going to have trouble doing that. Plus dot 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 plus n minus 1 times n times c sub n times x minus a to the power of n minus 2 plus dot dot dot. All right. Once again, if we let x equal a, then we get f double prime of a equal to 2 times c sub 2. So if you guessed f double prime of a was just going to be, or rather c sub 2 was just going to be f double prime of a, you're a little bit off. As I said, it's just not quite that simple, although it's not overly complicated. So solving for c sub 2, because again, we're actually looking for the coefficients here. C sub 2 is going to be f double prime of a divided by 2. I encourage you to try to guess what c sub 3 is going to equal and try to make it as general as possible. If you're going to, well, after your guess, then try to make it as general as possible so you can see what the rest of them might look like. And if you can't guess it correctly, that's okay. We're going to work it out, and you'll be able to see it. All right, f triple prime of x. Got to keep going here until we can see the pattern. 2c sub 2 is a constant, so its derivative is 0. And then we're going to be left with 2 times 3 times c sub 3 plus, again, I'm not going to simplify, 2 times 3 times 4 times c sub 4 times x minus a plus, what would the next term look like? Well, the next term, well, hopefully I'll get this right, but it should be 3 times 4 times 5 times c sub 5 times x minus a squared plus dot 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 plus, and then I'm gonna write this kind of so it overlaps down here. We're gonna have n minus 2. I like how I say 2 and write 1. N minus 2 times n minus 1 times n times c sub n times x minus a to the n minus 3, and then plus dot dot dot. Now again, let's let x equals a, And then f triple prime of a is going to equal, again, every term after the first constant term there is going to go to 0, so I'm going to get 2 times 3 times c sub 3. And so c sub 3 is going to be equal to f triple prime of a divided by 2 times 3. I hope you can see how this is going to generalize. If you can't, let me give you one more hint, but you might want to pause the video if you still want to think about it for just a moment. 2 times 3 on the denominator is the same thing as 1 times 2 times 3. That's a pretty good hint right there. But I'll forego saying it specifically until we do it one more time. So remember, for anything past the third derivative, we stop using the tick marks and we start using numbers in the superscript position, upper right hand, in the exponent position, if you will, but it's technically a superscript. But we put parentheses around it to indicate that's the fourth derivative, not the fourth power. And then this is going to be of x. And then we're going to be left with 2 times 3 times 4 times c sub 4 plus, we're going to have 2 times 3 times 4 times 5 times c sub 5 times x minus a. I'm not even going to do the next term here. I'm running out of space anyways. Let's just get to the general term. So n minus 3 times n minus 2 times n minus 1 times n times c sub n times x minus a to the fourth plus dot dot dot. Barely squeeze onto the screen there. And one more time, let's let x equal a. And when you do that, your fourth derivative of f at a is going to be just 2 times 3 times 4 times c sub 4. Every other term goes to 0. And so c sub 4 is going to be equal to the fourth derivative of f at a divided by 2 times 3 times 4. Or again, as the last hint, 1 times 2 times 3 times 4. Hopefully you recognize this already, but I'm going to put it explicitly now. 1 times 2 times 3 times 4 is just 4 factorial. And that's the same thing up here. The c sub value of c sub 3 is f triple prime of a over 3 factorial. Does that hold up here? Well, 2 is 1 times 2, so this is the second derivative of a over 2 factorial. So that still works. If I go way back up here, well, c sub 1, it is true that c sub 1 is f prime of a divided by 1, but that's just 1 factorial. So it holds, it works. So what is the value? Let's actually put 3 dots here. So if I look at the nth coefficient, well, that's going to be the nth derivative of f evaluated at a divided by n factorial. Now we know all the coefficients. Well, we know most of the coefficients. I kind of neglected going all the way back up to the top for a moment. What about c sub 0? We said c sub 0 is equal to f of a way back at the beginning. If we follow the pattern, then this should be equal to f of a divided by 0 factorial. How does that make any sense? Well, I told you guys a while back that I would explain to you why 0 factorial is equal to 1, and here it is. This is why 0 factorial is equal to 1, so that this pattern holds. Mathematicians, create the mathematics that they want, and they want patterns to hold. Now, of course, if you create bad mathematics that doesn't model the real world in a way that is useful or serves whatever other purpose the math was created for, then you make it whatever you want. Doesn't mean it's good mathematics. But in this case here, mathematicians define 0 factorial to be 1 so that this pattern in the Taylor series, oops, I dropped a phrase here. This is going to be our Taylor series. So that this pattern in the Taylor series holds, so that the coefficient of the nth the nth coefficient is equal to this expression.